Okay, so we only did a little bit of enzymes last time, maybe just half an hour worth of lecture. So, are enzymes proteins?
Yes.
Except for? Huh? Ribozymes, but we don't care about ribozymes, but food enzymes are proteins. Okay. So what's the definition of an enzyme and its function? What is an enzyme? And why do we use it? So it's a biological catalyst, and what does it do to the reaction? Lowers the activation energy of the reaction, so speeds it up. Okay. So we talked about 6 classes of enzymes. Do you remember what they were? Or an example of it?
Oxidoreductase, transferase.
So oxidoreductase, transferase, hydrolases, isomerases, lyase and ligases. Okay, so oxidoreductases, they catalyze oxidation reduction reaction. Transferases, they catalyze reactions that involve transfer of functional group from one compound to the other. Isomerases change one compound to its isomer, such as glucose to fructose. Hydrolases obviously breaks a covalent bond, utilizes H2O or water, and uses the elements of water as components of the products. Lyase form or break down double bond without the use of water, and ligase form a covalent bond with the use of ATP. I think that was all. So what do we know about enzyme specificity? What does it mean when we say enzyme specificity, and what's the induced fit theory?
For the induced fit theory, it means that environmental conditions play an impact on how the enzymes bind to their substrates. And
Yes.
so I guess the specificity means that they have specific shapes to fit with their substrate, but they're not always that shape, same shape.
Exactly. So stereochemical binding, where the active site binds specifically to a substrate due to a certain shape of the active site. However, the active site is not rigid like the key unlocking key theory, which was originally thought as it is a fixed shape. It's actually a shape that changes and molds to the shape of the substrate and is impacted by environmental factors. That's why there's optimum pH and optimum temperature, optimum water activity, and ionic strength that impacts the shape of your active site. And that impacts the activity and the specificity of the enzyme to the substrate. So we talked about different applications of enzymes, and we talked about applications related to quality, to activity, and to analysis of constituents, and as processing aids. Can you recall some of the examples for enzyme applications in food? Try to recall without looking at your notes, and I'm sure you know without looking at your notes. Okay, Lisa.
Alkaline phosphatase is used for thermal degradation in milk for pasteurization.
So, testing the pasteurization of milk, we determine the activity of alkaline phosphatase to determine whether or not pasteurization was accomplished. Okay, other examples?
Processing aid or pectinase for clarification.
Okay, processing aid using pectinase for the clarification of apple juice, for example, making a clear apple juice. Other than that, I think Jason gave a nice example last time. related to meat.
Oh, yeah.
What was it?
Enzymes to tenderize meat.
Yeah, tenderization of meat using papain or bromelain. What other? Where do we use enzyme as processing aid? Very common. We eat it almost daily. Almost. Cheese. Well, at least I eat it almost daily. Cheese production, we'll talk more about that when we do make. Huh?
What we use also commercial enzymes for oil deguming.
Yeah, that's a processing aid.
Processing.
Very, very good. Thank you, Sir Paul. What else?
Analysis of constituents would be alpha amylase in flour protein.
Analysis of constituents. Alpha amylase, we analyze it in flour for quality.
Quality.
We analyze alpha amylase to determine the activity, determine if starch has been broken down and will impact viscosity. But as an analysis of constituents, for example, determining glucose or determining total starch, we use enzyme kits to allow us to do that. So it's kind of used for analytical purposes in this case. So there are many examples, obviously, and we will be giving a lot of those. All right. Can you define Vmax? What is Vmax? We started talking a little bit about it. I know you had the exam and you were all tired, but you remember at all what Vmax is? From its name, max. Maximum velocity. So it's the maximum velocity of an enzymatic reaction, and it's impacted by several factors, and we'll talk about that. So can you remember Km?
Constant, which happens at Vmax by 2.
Huh?
Which happens at the rate maximum by 2.
What happens? The Km
Km is equal
to the substrate concentration at Vmax by 2. Okay. And it relates to the affinity of the enzyme to the substrate. Okay, we'll talk more about that. I don't know, did I talk about this curve last time? Not yet? Okay, I'll get to it then. And we talked about the importance of enzyme kinetics, and that's why we're going to spend some time talking about enzyme kinetics. Why is it important to understand enzyme kinetics? So with enzyme kinetics, we can get characteristics such as Vmax, Km, impact of inhibitors on the Vmax and Km, impact of substrate concentration, impact of enzyme concentration. Why is all this important for us in food systems that utilizes enzymes? Yes.
To know how much enzyme you'll need.
Exactly, yes. If we were using it as a processing aid, how much rennet do I need to produce a certain amount of curd in a certain amount of period of time? So I really need to understand that. If I want to inhibit a certain enzyme, I want to inhibit polyphenol oxidase. I don't want polyphenol oxidase to cause browning in certain application. So I need to understand what inhibitors I can use to increase Km or reduce Vmax. So I really need to understand the enzyme kinetics of polyphenol oxidase, probably from different sources, in order to inhibit its activity. Or to design an enzyme assay. In order to design an enzyme assay, I really need to know what concentration of substrate will result in saturation of the enzyme, what concentration of inhibitors I need to add or not have in my system, or what concentration of cofactors, which are enzyme activators, that I need. So I really need to understand kinetics to design any enzymatic reaction, whether in a lab, on a lab scale, or whether on an industry scale. It allows me to design my trial or my experiment. So that's why it's very important. Any particular question before moving on in the enzyme area? I know we didn't cover a lot, but do you have any pressing question before moving along? Or not pressing, any question? Okay, we'll start fresh. So enzyme kinetics. So we talked a little bit about this figure last time and described it. I will remind you, refresh your memories. Okay, so Whenever we have an enzyme reaction, usually we monitor an enzyme activity or enzyme reaction in general. We monitor that by more often time measuring the product. So by measuring the concentration of the product, we can plot the concentration of product over time. And we plot the data at certain time points, and then we see a curve like that. This curve starts with the pre-steady state, and this is just the formation of the ES complex. It takes milliseconds to actually start forming, and then you will have E plus S gives you the ES, and the rate constant is K1, and then ES can go forward and produce product, which we measure, and this rate constant is K2, but it is irreversible interaction, so ES can go backwards. That's why if we saturate the enzyme with substrate, we get the maximum rate for the reaction, because you always have additional substrate. When you have E that is freed upon product, there is enough substrate for the E to bind to S, form the complex, and continue the reaction. Okay, so the pre-steady state is where we actually bind the E and S and form ES, but once it's bound, we enter a steady state, which is the concentration or rate of disappearance of ES equal rate of appearance. So that means rate of disappearance, the K minus 1 plus K2 equals K1. Okay, so it's being produced and it's disappearing in this direction. In this case, here we have a linear relationship, and the slope of that line is your velocity, or we call it the initial velocity. So at a constant or at an X concentration of a substrate, you use a substrate, you use the concentration of an enzyme, put them together, and then this is what you get. And you get the initial rate of the reaction. So, and then eventually the linear lines start curving and you get kind of plateaus off. And do you remember why we said last time this happens? Why doesn't it stay linear all the time?
The substrate starts to run out.
Yeah, depletion of the substrate. So as the reaction continues and progresses, the substrate will be depleted, and then ES will start going more backwards because you don't have enough of substrate to produce ES complex as much as you had before. So when we want to monitor enzyme reaction, the best way to ensure monitoring it is during its steady state, so we can actually get a velocity of a linear curve. Okay, so that's the initial velocity, and if we run the same reaction at different concentration 0, 1, 2, 3, 4, whatever, molar, millimolar, micromolar of your substrate concentration. Every time you run the reaction, and if you run it at a different substrate concentration, you get different velocities or initial velocity. If you plot the velocity of different reactions against the substrate concentration of these different reactions, you get this kind of a curve. And from there, you can get the Vmax. The Vmax, it happens at high concentrations where the substrate saturating the enzyme, or the enzyme is saturated with the substrate. No matter how much you add more substrate, at a particular enzyme concentration, you kind of reach maximum reaction rate. It won't increase anymore. And then from there, we can derive the Km, which is the substrate concentration at Vmax by 2. So the concentration of the substrate where the rate of the reaction is Vmax over 2. And we said that this is important characteristic that relates to the affinity of the substrate to the affinity of the enzyme to the substrate. So if you look here, I have substrate 1, the red, and substrate 2, the blue, and the same enzyme. Okay? By looking at this curve, taking that moment to look at this curve and tell me which enzyme, which substrate the enzyme has higher affinity to. The red substrate or the blue substrate, by just looking at Km and analyzing the sphere. Where do you have higher affinity, with substrate red or substrate blue? Do you want to say something? The red one, why?
Just faster.
Faster. So you reach Vmax by 2 at lower substrate concentration. So you reach the same velocity. Here lower substrate concentration, and here you need higher substrate concentration to reach that same velocity, Vmax over 2. So obviously, this substrate, the enzyme has higher affinity to. So lower Km implies higher affinity. The lower the concentration where you reach the same velocity, or Vmax by 2, would mean higher affinity of the enzyme to the substrate. Okay? So Vmax is impacted by nature of the substrate, obviously, and enzyme concentration, the conditions of the reaction, as well as presence and type of inhibitors. So Km is not necessarily impacted by enzyme concentration. It's impacted by all other factors, substrate and type of enzyme and type of substrate, obviously. And then the conditions of the reaction, pH and temperature, as well as inhibitors. So the concentration of the enzyme does not impact its affinity to the substrate. Okay? But obviously the type of enzyme or the nature of the enzyme. All right, so what are good consequences and bad consequences of a low Km? So in an application or food application, low Km is desirable when we are producing a product using enzymes. So if I want to produce a corn syrup, a 40-DE corn syrup, so I need high efficiency for production. So I need to get an enzyme and a substrate combination where Km is low. This means I reach the high rates faster and I have increased productivity. So I produce more in a shorter period of time. Okay. So I would choose an enzyme, if I want to choose an enzyme to produce 40-DE corn syrup, it's starting with the same substrate, so I would choose an enzyme that will give me lower Km so that I have higher production, higher productivity. Okay. So bad consequence when we have low Km is that when we have reactions that we don't want it to happen. So we don't want browning, we don't want enzymatic reaction. So when we have Km that is low, in this case would be detrimental. So we have high rate at low substrate concentration. So this is not something we want, and in this case, we will add an inhibitor to inhibit that reaction. Okay, so let's dive a little bit into first order and zero order from looking at this curve. So if I look at the substrate concentration, and if I'm really at high level of substrate, enzyme is saturated. So you can see here this plateauing effect. So between this point and this point and this point and maybe another point over there, do I see an impact of substrate concentration on the rate of the reaction? There is no more impact. So at high substrate concentration, there is really no more impact on the rate of the reaction. I'm maxed out. So at very high substrate concentration, that means substrate concentration much greater than Km, I have zero order reaction with respect to the substrate. That means no matter how I change the substrate concentration or increase it, my rate of the reaction will no longer impact. That's 0 order. However, at very low substrate concentrations, like here, you can see linear, kind of a linear curve. That means as I increase or change the substrate concentration, my rate of the reaction is directly impacted. So at concentrations much less than Km, I have first order reaction with respect to the substrate. So in this case, when I'm designing an experiment and I'm using this experiment to determine glucose content, for instance, that means I need the reaction to be sensitive to the substrate concentration. So I need to work in this area of the curve. I'm measuring glucose, substrate, and I care about the substrate or sensitivity of the reaction to the substrate concentration. So I use this place where to measure substrate concentration. So I want it to be first order with respect to substrate. So I make sure I have an abundance of enzyme so that my reaction is 0 order with respect to enzyme, no more impacted by enzyme, but it's impacted by the substrate concentration. On the other hand, if I want to measure enzyme activity, I want my reaction to be sensitive to the enzyme activity. I want to make sure that my concentration of the enzyme is high enough, and I need to know the Km. That's where it's important to know the Km of my enzyme with respect to that substrate. So I would design my experiments where substrate is in abundance, then any change in enzyme activity or concentration will impact the rate of my reaction, the rate of the reaction. So when I'm measuring enzyme activity, I want it to be 0 order with respect to substrate. When I'm measuring substrate activity, I need it to be first order with respect to substrate. And that is an example of why it's very important to know the Km value so that I can design my experiment, whether I want it to measure substrate or enzyme activity. All right, this is your favorite part, deriving the Michaelis-Menten equation. And why it's important? Because the Michaelis-Menten equation allows me to determine Vmax and Km, which are important parameters, or catalytic efficiency, which I'll talk about later, which are important parameters in designing enzymatic reactions or inhibiting an enzyme reaction. Okay, so I'm going to start with the velocity of the reaction for the production of product. So this way, from here to here. So the velocity is equal K2, which is the rate constant, by the concentration of the enzyme substrate complex. So that is my first equation. So I want to look at the steady, I want to analyze things at the steady state. So what's the rate of disappearance and the rate of appearance? So rate of disappearance of ES equals this reaction and this reaction. So rate constant -1 going backwards times the concentration of ES plus the rate constant going forward multiplied by the concentration of ES. Rate of appearance, so the appearance of ES is only 1, is this, which is the rate constant K1 into the concentration of the substrate into the concentration of the enzyme. So in that steady state, and that's where we have to measure or have all of our enzymatic reactions in that steady state here to get the initial velocity to apply here. So in this area here, we have rate of disappearance equals rate of appearance. So I put this equals to this. So I want to solve for ES. So I will look at how do I get rid of just E in this case. So E0 is the total amount of enzyme at any point in the reaction. Total amount of enzyme equals enzyme that is free, whether here or after the product was formed, and the concentration of the ES complex. Then I substitute E. So E equals E0 minus ES. And then I just substitute the E in this reaction. That's the only thing I did differently here, is I substituted so I have ES in my equation. So here, another substitution, so derivation, substitution. So ES goes out because it's common, and this K minus 1 plus K2. That's the only change in this equation. And then I'm solving for ES, just mathematical formation, just to solve for ES. So I have ES, and I just rearrange my values to solve for ES, and I get this factor here, which is a constant. And this factor here, which is the constant, K minus 1 plus K2 over K1, is my Km, is the Michaelis-Menten constant. So this value, it's the same equation from the previous page. This here is my Km. Okay. So going back to my initial equation, which is the velocity for the product formation is equal to the rate constant K2 by the concentration of the ES complex. So if I want to solve for the velocity, now I have solved for ES here, I substitute. So instead of ES, I put my equation here. So now I have Km and velocity in my equation. Okay? So you see where I'm going with this? So the ES from my original equation, since I solved for it here, I just took this value and replaced it here. Same. When all the enzyme is saturated, we have Vmax, right? So at Vmax, this is the equation for V0, initial velocity at any concentration of the substrate. But when we have substrate saturating the enzyme, we have Vmax. So when we have Vmax at concentrations much greater than Km, the concentration of the enzyme, all of the enzyme here is saturated with substrate. So my enzyme total concentration equal the concentration of ES, because all of the enzyme is in this form now. It's saturated. Okay? So when I have Vmax, then I have this equals this, because all of my enzyme is saturated. You can stop me at any point if I'm confusing you. Then, at this point, I have Vmax equal K2 into the whole concentration of the enzyme. So, and V0 then equal Vmax. So K2 into enzyme total is now Vmax, right? So did you follow how this Vm became here? It becomes here because at Vmax, all of the enzyme is in this form. So K2 into enzyme concentration total gives me Vmax. So now I have an equation that has three different things in it. So you have initial velocity, or 4. initial velocity, Vmax, Km, substrate concentration. If you think of an equation of a line, which we'll get to that in a minute, in an equation of the line, when you have data and you plot your data and you get y equal ax plus b. So this is your dependent variable. This is a slope. This is your intercept. This is your concentration. Okay? So I have 1, 2, 3, 4 variables. And here are my variables. V0 is a variable, dependent variable. It is dependent on the concentration of the substrate. And then I have two values that I need to be solving for. And they're integrated in an intercept and a slope. And I'll show you how that is in a minute. So this is the Michaelis-Menten equation that we will use when we plot our data from an enzymatic reaction to calculate Vmax and Km. But this doesn't look like y equal ax plus b. This is obviously not a linear curve. So my Weaver plot is. So another group of scientists said, okay, we like working with linear curves because linear curves are easy. We get this equation and we can solve for unknowns from this equation. So what they did, they took the Michaelis-Menten equation, inverted it, and they found a linear relationship right there. So the inverse of the Michaelis-Menten looks like that. 1 over initial velocity, Km over Vmax, into 1 over concentration of the substrate, plus 1 over Vmax. So now this is your intercept, right here. That's your intercept. 1 over Vmax. Your slope is Km over Vmax. Km over Vmax. Your x is 1 over the substrate concentration. 1 over the substrate concentration. So your x here is 1 over the substrate concentration. Your y is 1 over V0, which is your dependent variable. And then b is your intercept, which is 1 over Vmax. So if you have your equation of the line, you get the b, which is a value that you will replace and you can calculate Vmax. And when you have Vmax, you can calculate Km because the slope equals Km over Vmax. So from your equation, you get the slope, you plug it here, and you have the Vmax from the intercept. Then you are able to get the Km. Now, how do I get my plot in the first place? How do I get this equation in the first place? So I run my reaction at one specific concentration of the enzyme. So I start at 10 millimolar, for example, and run my experiment or analysis, and then I determine the slope here, which is my V0. And then I run the reaction again at another concentration of the substrate, which is, let's say, 15 millimolar. And again, I plot over time my product concentration of that reaction, and I got another V0. I do that at least 5 times so that I have 5 points that I can plot. So I take the inverse of the initial velocity by the inverse of the different concentrations. So at least 5 different concentrations so that I can have good prediction of the line and good R squared. Then I will get this equation. And from there, I can plug in my values and determine Vm and K. Okay, any questions? No? That's okay, don't be shy. I don't expect you to know this. Although you've seen it probably multiple times before. What did I do? Okay, no question? Moving on. So this is an example where I had applied the Michaelis-Menten equation and Lineweaver-Burke plot. So I was doing research at Purdue, and I was looking at the bioactivity or bioavailability of 3 compounds. These are phytochemicals present in soy. So they have physiological benefits. So they can be antioxidants, they can be, well, mostly antioxidants. So they have physiological benefits, basically. And I wanted to look at how bioavailable they are. The body will not absorb them in this form. They need to be absorbed after they're broken into a product. And the way they are broken into a product is using an enzyme. So this is a compound, one of them. The R and R2 R1 and R2 are different based on the different compounds. And there is a glucose. So the enzyme, it's a glucosidase. That means it breaks down a glucose unit. And then we have this that can be absorbed by our body. So I was looking at the activity of the enzyme towards the 3 of those to determine which one is more bioavailable than the other, which one has more bioavailability. Then I ran the analysis at different concentrations, at least 5 different concentrations of each of those. So 1 diazine, genistein, and glycitin. Okay. By looking at this, can you tell me which of these would be more bioavailable or least bioavailable? Can you predict based on what you see? Look at Km, look at the Km is the intercept here, or 1 over Km is the intercept. And here 1 over V max is the intercept. So the glucosidase enzyme has the least affinity to which of those, or the highest affinity to which of those? Vaidi, you want to give it a go?
Glycitin is the least.
Least bioavailable, yes. Glycitin is the least bioavailable because if you just look at the Vm, the intercept, so this has higher value. 1 over Vm has higher value here. That means Vm is smaller, right? Because it's the inverse. So high here means smaller Vm. Okay? Whereas for these 2, we have a lower value. That means the Vm is higher. So this had higher slope. That means Km over Vmax is higher value. So that means Km is higher. So we have higher Km and lower Vmax. So higher slope. So the higher the slope, the lower is the activity in this case of the glucosidase enzyme to that substrate. Okay? So this to show you that is one application where this has been useful. There are many other applications that you'll see later. So glycitin is the one that has low Vm and low Kcat over Km, which is the catalytic efficiency. So the higher the rate per a set amount of enzyme means higher catalytic efficiency. But when we have high Km and low Vmax, that means the catalytic efficiency is low. For the glucosidase enzyme that breaks this and makes that available or bioavailable for absorption. Okay. So factors that affect the enzyme reaction rate. So we have several factors that affect the enzyme reaction rate, and one important factor is enzyme concentration. So theoretically, there is a linear relationship between enzyme concentration and velocity. So as enzyme concentration obviously increases, we have higher rate or higher speed of the reaction. And in this case is when the enzyme is saturated with the substrate. So that means we don't have the substrate as a limiting factor. If we have the substrate as a limiting factor, no matter how we increase the enzyme concentration, we're not going to increase the rate because we don't have enough substrate. But when we have enough substrate in the system, then the reaction is first order with respect to the enzyme. As we increase enzyme concentration, the velocity of the reaction is higher. So this is to illustrate that this is a prediction. So as we have what happens as a particular enzyme concentration, you would see that there is a linear increase. But in reality, the concentration of the enzyme over time is going to change. So it won't be linear. So what does that mean? So let's say we are designing an experiment, and to make it efficient, maybe 10 minutes is enough. It would be too short of a period of time to monitor absorption or do anything if it's 1 minute. And it would be too long if my reaction is 2 hours. So I need to find a time that actually gives me good prediction in a reasonable amount of time. So 1, 2, 3, and 4 are the enzyme concentrations. One enzyme concentration, a higher enzyme concentration, a higher and a higher. So let's say my time point that I'm comfortable with is 10 minutes, and it's right here. So if I choose concentration 1 or 2, the predicted line is similar to the actual here. It's still linear. So I can get my initial velocity and there's no problem. But if I use a higher concentration of enzyme, I no longer have the correct prediction because now my slope is not linear in reality. It's not linear like here. At time 10 minutes, I need to go to 1 minute probably. And it's too short of any reaction time. So therefore, I'm not going to use the concentration 3 or 4 for the enzyme. I might go with 2 or 1. But I will go with 2 because this might be higher absorption. So it would be better for me to work in that range rather than in this range would give me very small concentration, very small or low absorption that would be close to the noise of my equipment. So I don't want to work here. I don't want to work at a very low concentration. So I would say in this case, I'm going to go with enzyme concentration 2. In 10 minutes, I have good prediction, linear, steady state, and I get my slope that I will use for the Michaelis-Menten equation. Okay? Yeah, this is just to illustrate that we always want to work in the steady state where we have a linear line, and so with that we can get the slope, which is our initial velocity. Okay, substrate concentration is another factor that impacts the rate, obviously, and we can either have first order working here or zero order working here. So we really need to determine based on what we are looking at. Are we looking at enzyme activity, measuring enzyme activity, or measuring substrate changes in substrate concentration? So that's the saturation effect. So you also can have substrate inhibition or substrate activation. Substrate inhibition sometimes happens when you have a high concentration of a substrate, really high. The substrate is binding not only in the active site, but is binding in a different location on the enzyme as well. And once it binds at a different location on the enzyme, it can have two impacts. It can either cause activation, that means making sure that the active site is in the correct format for the substrate to bind, or it can actually change the active site shape by binding to that enzyme, changing the active site shape, so the active site shape no longer can bind to the substrate itself. So these can happen. All right, temperature effect, which you're familiar with. There is an optimum temperature for the enzyme, or for any reaction. When you increase the temperature, you increase the kinetic of the reaction. So you would start off, say, a higher velocity with higher energy, higher temperature. However, since enzymes are proteins, you reach to a certain point, and then you see a real drop, a very significant drop in activity after a certain temperature. Why is that? So you continue to see an increase, you reach to a really good place of high viscosity, velocity, and then you reach to a temperature where the protein denatures and then no longer active, and we see a steep drop in velocity. So it will not indefinitely increase. So the pH, and this is just an example. It doesn't mean, please do not think that all enzymes are most active at pH 6. Okay? This is not true. Pepsin, for example, is active between 1.5 to 2 pH. So it's really not the point. The point is it's a bell shape. So again, you have an optimum for each enzyme, and the optimum for that enzyme is based on what's the best ionization state for that enzyme to bind to a substrate. So depending on the substrate, depending on the enzyme, that optimum can vary. Okay? But when you deviate from the optimum, you change the ionization state of that enzyme in a way that it's not very desirable for binding to the substrate. Okay? So that's why we have optimum pH, optimum temperature for each enzyme. Because remember, with temperature, you get denaturation and it's no longer active. And with pH, you get away from the best ionization state. Now, sometimes you hear the word pH stability versus optimum pH. So, what does that mean? The enzyme might be stable at a particular pH, but not necessarily that active. Okay? So, you can inactivate an enzyme by changing the pH. Some enzymes are very sensitive to pH, so you can actually inactivate them at really high pH or really low pH. The way to test that is to know at which temperature or at which pH, the enzyme becomes inactive. You can place the enzyme at different pHs and then bring it back to its optimum pH and measure activity. If the activity declined even at optimum pH, that means you destabilize the enzyme by putting it at a very adverse pH condition. For example, here trypsin is stable at pH 3, but optimum activity is pH 7 to 8. So you can bring down the pH and trypsin is still there. It's still relatively stable, not necessarily active, but still stable, not denatured. When you bring it back to 7 or 8, then the trypsin acts again the same way. Other factors, you need sometimes activators. So it could be prosthetic group That means it's a non-protein portion of the enzyme, and it binds almost irreversibly with the enzyme. It maintains the conformation of the enzyme to allow the substrate to bind to it. A coenzyme is dissociable. That means it binds and unbinds to the enzyme. It's not irreversible, it is reversible. And an example here is NAD, which is needed for alcohol dehydrogenase to produce an aldehyde, acetaldehyde, which is a dehydrogenated form of ethanol. Okay, this is another example of a coenzyme, which is an organic coenzyme, where you have, this is the active form of vitamin B6, and the enzyme that needs it is aminotransferase enzyme, which can cause deamination or decarboxylation or an anomerization, or changing or producing anomers. Other factors, inhibitors, presence of inhibitors. We have two types of inhibitors, or two categories of inhibitors. Irreversible inhibitors, once they're there, they bind, and there's no way they will be released. That means their dissociation constant is very, very small. What does the dissociation constant mean? Is the concentration of the free form of the inhibitor when the enzyme is present. When the enzyme inhibitor is present, it binds, and it will not be released very easily, so that's why we call it a reversible inhibitor. So the decrease in activity is directly related to the amount of inhibitor added, and there is the reaction is slow. For the inhibitor to react with the enzyme is very slow. So if we want to test the presence of alpha amylase inhibitor in legumes by an assay to determine the presence of the inhibitor, the assay requires that you have an amylase in the substrate, and then you add an extract from the legumes to determine whether or not you have that inhibitor. If you put the extract with your enzyme and substrate right away, you won't necessarily see a measurement or see an impact on the enzyme activity. You have to let it react, so you have to put the extract with the enzyme before adding the substrate for a little while so that they take time to interact. And then you add your substrate and you measure the activity to determine whether or not there is in fact alpha amylase inhibitor in the legumes. The other category of enzyme inhibitor is the reversible inhibitors. And these are important because we use them quite a bit in food systems to inhibit enzymes such as polyphenol oxidase enzyme. So we have different forms of these reversible inhibitors: competitive inhibition or competitive inhibitor, non-competitive, and uncompetitive. So these are the three different forms of reversible inhibitors. So the competitive inhibition here, in this case, let's say we have an enzyme specific to succinate, and then once the enzyme and substrate bind in a very stereochemical form, so you will get the substrate converted to a product, fumarate in this case, and the release of the enzyme. A competitive inhibitor, in this case, is malonate. It has a very similar structure. The only difference is a methyl group is lacking. Because of its similarity to the structure, it still can bind to the active site. So now succinate and malonate are competing for the active site. That's why we call it competitive inhibition. So they compete, and then what happens is you have a reaction here that does not produce a product. So you have less production of fumarate in the presence of an inhibitor. unless you really have high concentration of substrate, that means that if you have much higher concentration of substrate than the inhibitor, then the reaction will be this way more than this way. Okay? This is an example of the graph that you would get, Lineweaver-Burk plot, when you have competitive inhibition. So here's the reaction and the slope without the inhibitor, and here's the reaction and the slope with the inhibitor. You can see this slope is steeper. And what happens here is your intercept is the same, but the Km value is different. So with competitive inhibition, you impact Km, but the Vmax is not impacted. So when you want to determine what type of inhibition, you add different inhibitor with your enzyme, and you want to determine is it competitive, non-competitive, uncompetitive. You plot it and you can see, oh, I have similar Vmax, but the Km is changing, higher slope, which means Km over Vmax is higher, that means Km is higher. That means this is a competitive inhibition because the enzyme is, the Km is the enzyme, is the factor that is impacted by competitive inhibition. So we lose affinity to the substrate because there is a competition with another compound in the system. So when we have a competitor, that means a good competitor, when we end up having higher Km value in the presence of the inhibitor, so we need more substrate to slow down an undesirable reaction. So we need more substrate, and it slows down an undesirable reaction unless substrate concentration is very high. So in this case, if we have reasonable amount of substrate and you add that inhibitor, it slows down the reaction. However, if we have really high concentration of substrate, it won't matter if you add an inhibitor unless you add a really high concentration of inhibitor, which could be expensive. You cannot do that. In case of undesirable competitor, in this case, you need more substrate. It slows down a desirable reaction, making yield less, and then amount of substrate converted per hour is less. In this case, you want to get rid of that inhibitor. You want to remove that inhibitor from your system so that you have better productivity.
So both are having the same symbols, is that right? If Km is greater than Km.
Yeah, but in one case, it depends on your purpose of using those inhibitors. Sometimes you want the inhibitor there to inhibit an undesired reaction. Sometimes you do not want it there because that will cause a loss in productivity. So sometimes it's good, sometimes it's not good. Non-competitive inhibition. In this case, your inhibitor is not competing for the active site. So it does not have a similar structure to the substrate. In this case, it binds at a different spot on the enzyme and results in change in the active site, and this will make it the substrate can't bind anymore. So in this case, the affinity is not impacted, but what's happening here is the velocity of the reaction is impacted. So here we see the slope is higher, not because Km changed, it's because Vmax is lower. Or Vmax is lower. So when Vmax is lower and Km is the same, we still see a higher slope. So in this case, it is non-competitive. Lastly here, before I give you a few minutes a break, is the uncompetitive inhibition. And here, what happens is the enzyme still has an affinity to the substrate, it still binds, but the inhibitor binds when ES complex is formed. Once ES complex is formed, the inhibitor binds and then prevent the reaction from going forward to a product. In this case, we don't see, we see a parallel shift in the line reverber. So going from here to here, that's the parallel shift. Okay, so I'll give you a break, 5 minutes, 3 minutes break, stretch, walk, and come back.
My question is mainly about math. For the competitive is, so we see like, when the slope is higher, that's Km is higher, right? Max. But if we see like from here, if minus Km1 and the reciprocal of that.
So it would be, the absolute value.
Oh, yeah.
The absolute
so
value, not the negative or the
negative.
positive.
There is
The absolute value.
Yeah, I know that.
I don't know, it's just the absolute
Yeah.
value is what you take. So,
Yeah,
so here 1 over Km versus
Yeah.
1 over Km.
Yeah.
But the
So,
absolute value of
this
that,
is-
the Km value, and then that one, that's the value. Yeah, whether it's in the negative or not, doesn't matter.
Oh,
But this number in absolute is smaller than
Yes.
this number.
Yes,
Because of the Km.
yeah, but we can now just do the exact number. Why is that? From the equation, it shouldn't matter, right? I mean, is that like whether it's an absolute or not? 'Cause,
No, it doesn't,
like, I mean,
it's negative Km,
Yeah,
negative
yeah,
1.
yeah.
So the negative 1 is mad, but the Km is Km,
yeah,
is the value.
yeah.
And
But-
then,
And then, if we just compare the intercept,
you're overthinking it. You're
Oh.
overthinking it.
it's, yeah, just
The
Yeah,
Km
like-
value is not a negative number. Cannot be a negative.
that's positive. Yeah.
So, but the
Yeah.
negative 1 is
Yeah.
coming because it is
Because
it's a
we-
projector.
Yeah, we make it 0, so we got
Yeah.
the minus here.
Yeah.
And yeah, so yeah, it's always better to see from
The
the slope, right?
Yeah, you don't get it from here, you get it from here. And use that value, and the
Yeah.
minus 1
Yeah,
is, the negative is coming from the minus 1 here, not the Km itself.
yeah. Thank you. Yeah, because I was like,
Yeah, you don't
that, and I'm
confuse it,
thinking
yeah.
like about KM. So why does it have higher KM? I feel like that's really, I mean, mathematically, I mean the K. So this is, so minus 1 over Km. That
In this case, there's no inhibition, right?
yeah,
In
yeah.
this case, there is a change in Vmax as well.
Yeah.
So even if in the here might seem as a smaller Km,
Yeah.
but the decrease in Vmax is higher. So it gave you a higher slope anyway. So here there is Vmax and Km
Yeah.
impact.
Yeah. Yeah.
The other example is the Vmax did not change.
Yeah.
So the
That's
change in
there
Km
too.
impacts the slope.
Yeah.
Yeah?
So they always, yeah, so they are always in the negative correlation.
Not necessarily.
Oh,
Well,
yeah,
yeah, sometimes your Vm is the same, but the Km is changing.
yeah,
So that impacts the slope. Sometimes both are changing. One
Yeah.
is decreasing, the other one is
Yeah, will
not
they always go
necessarily
that way?
increasing. Sometimes you don't
okay.
have to change. The Vmax is not always changing depending on the Km. Sometimes the Km doesn't change
Change
and the
it.
Vmax change.
Yeah.
Sometimes both are changing,
can they both change the same way?
both increase or both decrease.
Yeah, I feel this.
I don't know, it depends. It depends on whether we're looking at inhibitor presence or just the enzyme, how the enzyme might have a higher affinity, but yet lower Vmax because Vmax is impacted by the environment conditions as
Yeah,
well at the
yeah.
substrate
Yeah.
structure.
Yeah, so
Yeah.
they can
They can
change
be-
any of it.
Yeah, they're not like linked together.
Gotcha.
Okay. It gets so complex. Okay, so let's continue. Okay, this is recap questions for you to review for later. This is an example of an application where we wanted to look at the type of inhibitor that is natively present in milk. So this is another research project that I worked on, again at Purdue. And here what we did, we were looking at plasmin and plasmin inhibitors in milk. So plasmin is a native enzyme that is present in milk and can cleave casein and impact the quality of milk and the quality of cheese. But it's a very complex system in milk. There's also inhibitors in there. So we were looking at ways to inhibit plasmin or not inhibit depending on the application. So, but we wanted to understand the plasmin system in milk, so we wanted to understand the plasmin inhibitor activity present in that milk. Is it competitive? Is it non-competitive? What type of inhibitor it was? So we extracted pure plasmin and pure plasmin inhibitor from milk, and we ran the enzyme assay with and without the inhibitor. So we ran it without the inhibitor, only plasmin, and we had a substrate similar to casein, a synthetic substrate, and then we ran it in the presence of the inhibitor. And we determined the Km and Vmax and Kcat and the catalytic efficiency. And from what you see here, do you think plasmin inhibitor is a competitive or non-competitive inhibitor? Competitive inhibitor. So let's look at Km value. So the Km value increased. So it is here increased by about 5 times. Here it's -1, this is -2. Just it went from about 10 to 5. 0.09 to 0.5. And then the Vmax hardly changed, 1.36, 1.42 against times 10 to the -3 times 10 to the -3. So Vmax did not change here. Kcat remained the same, but when we got the efficiency of Kcat divided by Km, you see a tremendous decrease in the efficiency of the enzyme. So from there, we determined that the plasmin inhibitor present in milk is a competitive reversible inhibitor. And sometimes another application is we want to choose an inhibitor for an application to inhibit browning, for instance. In this case, polyphenol oxidase inhibition and the use of phenylthiourea versus para-hydroxybenzoic acid. So we wanted to determine the type of inhibition. So the para-hydroxybenzoic acid had a competitive inhibition. The other one had non-competitive inhibition. Km did not change, Vmax increased. So Vmax decreased, sorry. So here, lower rate means you need less inhibitor at any substrate level. So non-competitive inhibition is always better to use in an application like this. So because it's not impacted by the amount of substrate. Competitive inhibitor is impacted by amount of substrate. So if we have high amount of substrate, even if we add an inhibitor, it might not have a great impact because the substrate is present in abundance. So you need to add more of the inhibitor, and that becomes costly. So, but however, an inhibitor that impacts the actual rate of the enzyme rather than the affinity, so it is not impacted by the substrate concentration, would be better. Because that means you need less of that enzyme. But things to consider is what's the cost per gram added? Is it safe to use? What's the legal status? Do we need to put it on the label? How would that impact? And does it have any sensory impact in terms of flavor perception? So things to consider when choosing an inhibitor. So almost always measuring enzyme activity is based on measuring absorption of a substrate or of the product. So that's how we measure activity. Usually it's spectrophotometric methods, often. But I want to point out the difference between when we say units of activity, when we're measuring activity versus concentration of the enzyme, which is a protein. So you're looking at amount of enzyme in terms of protein. But often you are looking at the activity of the enzyme. And then the unit of activity, 1 unit for instance, it relates to an amount of enzyme that will result in the production or the conversion of 1 micromolar of substrate per minute at a specific conditions. That is what a 1 unit means. It means the amount of enzyme that results in 1 micromolar conversion of substrate per minute at a specific condition. So it's not a universal unit for all enzymes and all substrate under all conditions. It is impacted by the pH, it's impacted by the temperature, it's impacted by the substrate that you're using. So you often, when you buy an enzyme, you'll see on the specification sheet the units of activity. But it tells you how that unit of activity was measured. It tells you what substrate was used, what's the pH, what's the temperature. And that is what you really need to know in order to understand what the unit of activity means. So you cannot say, I'm going to use a different substrate and say my units of activity is this. But no, you're using a different substrate, you're using a different pH, you're using a different temperature. You cannot do that. You have to keep everything constant when you're measuring the unit of activity of a particular enzyme. Okay, so keep that in mind. If you ever need to purchase an enzyme, understand what unit of activity is. Make sure that you know that it's impacted by pH, temperature, the type of substrate. Okay. Oftentimes, another thing that is important to know is sometimes you need coupled reaction for measuring of a specific activity or measuring of a specific substrate. So it's not always one reaction, sometimes it's coupled reactions. With coupled reaction, what we mean is that you have the first reaction, which we call measuring reaction or auxiliary reaction, where your substrate of interest that you want to measure is you use an enzyme and you get a product. This product does not necessarily absorb light, so you can't measure anything. So you have to have another reaction which converts P1 to P2, and then here you can measure the absorption. So, because here where we get a reaction, where we get an absorption, we call it the indicating reaction. So you have the measuring reaction and the indicator reaction. So that's what we call. 2 factors we need when we are working with a coupled reaction or an assay that involves 2 enzymes. We have to be very careful in selecting those 2 enzymes that they have similar pH optima. Because you don't want to play with the pH. It might be problematic if one enzyme has a pH optima of 2 and another enzyme has a pH optima of 7. So you need to change the reaction condition, which might impact other components and result in interferences. And then the other factor that we need to keep in mind is E2 should not be the rate limiting. That means this reaction should proceed very fast. As soon as you have the product, this reaction should be faster. So the rate of this reaction should be faster than the rate of that reaction, as it is the indicating reaction. Okay, this is an example of a coupled reaction, and here let's say we're measuring glucose is our substrate, and then we have the hexokinase enzyme that takes a phosphate from ATP and give it to glucose to produce glucose 6-phosphatase. This is not absorbs light, so we take glucose 6-phosphate. We need the enzyme cofactor in this case, which will react, which is needed for the enzyme, which is glucose 6-phosphatase dehydrogenase enzyme, that will result in dehydrogenation of this product to give another product and result in a hydrogenated NADPH. And then we measure absorption, so NADPH, you can measure absorption at a specific wavelength, and that's how we can determine concentration. Okay. Classes of enzymes that are most relevant for us in food applications. We have two classes that we see common, and we're going to talk about them. That doesn't mean that the other classes are not common. For example, we use isomerase enzyme in production of high fructose corn syrup. But here we're going to talk a little bit more about these two classes that are important in food application. Hydrolases are really important, and they have several applications. Proteinases or proteases, pectinase, amylase, lipase, lactase, invertase. We have a lot of applications here. And the oxidoreductase, the glucose oxidase, phenol oxidase, and peroxidase. So these enzymes are also important in food systems. So what's the definition of hydrolase enzyme? Okay, spare you. Here it is. So it's an enzyme where water participates in the breakage of a covalent bond of the substrate, and the elements of water becomes distributed into the products. So in this case, triacylglycerol, in the presence of water and in the presence of lipase, will give you diacylglycerol and breaking one fatty acid. Or if you have the reaction proceed for longer, you can actually get 3 fatty acids and glycerol. So you can break off all the fatty acids. And each time, the H2O components would be distributed between the glycerol and the fatty acid released. So pectinase is a hydrolase, and we use it to clarify juices, for instance. And so pectin is in general used as a gelling agent, but can also act as thickener, water binder, stabilizer. So we have the low methoxypectins and the high methoxypectins. Low methoxypectin, that means we have less than 50% esterified. So here's your pectin. And then esterification is with a methoxy group here. If we break that, if we remove the methoxy group, we have COO minus. In this case, the COO minus can interact with calcium, and another COO minus from another pectin molecule can interact with the same calcium, so you can get polymerization and gel formation. So the degree of esterification can be reduced. So if you have a high methoxypectin, you can make it a low methoxypectin by adding pectin methyl esterase. Pectin methyl esterase is going to break the methyl group off and have more CO minus groups, so it will have more interaction in the presence of calcium. So we get higher viscosity and firmer jets. So we have different types of pectinases. They could be endo or exo pectinases. The pectinases break the pectin into the units, the separate units, which are glucouronic acids group. And this is a procedure we can use, for example, in purification of apples. So when you break that large polymer into smaller soluble polymers, you get that clean apple juice. So two types of enzymes that can either cleave when you have a methyl group, or it can cleave when you don't have the methyl group. So you have the polygalacturonase or the polymethylgalacturonase. Enzyme 2, both of them. And both of them can be used to make sure that you break down your pectin into soluble components, and thus you clarify your juice. So pectin methyl esterase also require water, and then you break the methyl group off, and then you produce low methoxypectin. And in this case, it is naturally present in orange juice. And if you ever see that your orange juice separated because the pulp sediment versus, and then you get it clear, this is something that you don't necessarily want to see. You want, especially in orange juice, it's different than apple juice. You like to have the pulp, the haziness is actually a good quality. So in order not to have that separation, there are treatments to inactivate pectin methyl esterases. So it would be beneficial to inhibit the naturally present pectin methyl esterases to prevent that separation you don't want to see in your orange juice. Because when you break down the methyl in the presence of calcium, you form those, the bonding, and they can form large polymers and can precipitate out. That's what happens. So here's a case study. There's this article where they looked at inactivation kinetics of pectin methyl esterases in orange juice, looking at impact of pressure and combined with temperature. So they looked at inactivation kinetics of using high pressure, 400, 500, and 600. M Pascal. What's the M for? Whitey. Mega. Okay. And then effective thermal treatment, looking at those different temperature combinations. So what happened here? They looked at. They found that when you have pressure at 500 or higher, you can actually see a reduction in the residual activity. So here they looked at temperature and pressure combination. They determined the d-value, which is the time needed to reach 1 log reduction in activity. And they found that they saw significant differences at 37 degrees and higher, starting with 500 and then 600 megapascal, resulted in quite a bit of impact. So the time needed to reach 1 log reduction was much lower at higher pressure, higher temperature combination. So that's just an example. So amylases, these are also hydrolysases. hydrolases, and in this case, amylases can be defined as alpha amylase or categorized into alpha amylase, beta amylase, glucoamylase, and polymerase. So they work obviously on starch subunits, amylose and amylopectin. Glucoamylase is an exoenzyme. That means it breaks one glucose unit at a time, and then from the terminal. And also beta amylase is an exoenzyme. However, it cuts 2 units at a time from the external, from the terminal ends. And because it cuts 2, it produces amylose. Alpha amylase is an endoenzyme. It breaks inside of the chain and produces dextrin or maltodextrin. Polymerase is also an endoenzyme, and it's very specific to the chain. So the alpha-1,6 linkage rather than the alpha-1,4 linkages. So the chains that branches, basically. The branches. Debranching. It's a debranching enzyme. So an application is production of high fructose corn syrup, for instance. So we start with the starch. We use alpha amylase, we get dextrins. We use glucoamylase, we get glucose. And then we use isomerase to convert glucose to fructose. And that is your high fructose corn syrup. Another application, lactase is used for production of lactose-free milk for lactose intolerance. So it converts lactose into glucose and galactose. So it's for lactose intolerance, people that cannot digest lactose. So they break it for them before consumption. Another one that is very commonly used is sucrase, which is also known as invertase. So it converts sucrose into glucose and fructose. And the common application is this cherry-colored chocolate. You want to keep that syrup within that chocolate liquid. You don't want it to crystallize over time. To reduce the crystallization rate, you break down the sucrose into glucose and fructose. So fructose and glucose do not crystallize as fast as sucrose would. So it will remain on the shelf longer with syrupy liquid syrup. So proteases, there are many applications for proteases that are used in industry for texture, flavor, and bioactivity. So we use proteases in curd cheese production. We'll talk about that in the dairy protein section. Meat tenderization, disruption of gels. When we don't want to form gels in an application, we add protease to break down proteins so they don't form gel. Aging of cheese, where protein is hydrolyzed and gives you the distinctive flavor of an aged cheese because of the production of the peptides. And sometimes we add proteases to weaken the gluten. If you have really strong gluten and you don't want that strong of elasticity, you can actually hydrolyze it a little bit to break that elasticity of the gluten for unique applications. Of course, proteases are used to produce protein ingredients as well as protein hydrolysates in industry for different applications, enhancing functionality, enhancing bioactivity. So they have multiple uses. And the proteases, there are so many different proteases and so many to choose from. This is just a few examples. It can be too much to handle sometimes. So what protease I need to use for what application. But usually what I want to point out here is different proteases have different specificity and activity, and they can be grouped differently based on, for example, if they are metalloprotease, that means they need a cofactor, which is a metal, that needs to be present for the enzyme to work. Or they can be cysteine proteases. There is a cysteine group in the active site. So they kind of are named differently based on what they require for them to be active. And sometimes they are classified based on their specificity. For example, pepsin is not very specific. It's an aggressive enzyme. It can break mostly peptides in general, and it is a digestive enzyme. We have it in our stomach to digest protein. Other are sometimes more specific. They cut at different locations based on the presence of certain amino acids. And for example, serine endoprotease is called serine because they have a serine hydroxyl group in the active site as well. So this is just very brief description. Lipases. So lipases has an impact on flavor in different applications, such as yogurt and cheese fermentation, because of breaking the lipid and giving off fatty acids, and that will impact flavor. Lipases are used sometimes to enhance emulsification, production of mono and triacylglycerols that are used as emulsifiers, tailor-made lipids for different functionality that can be used for their emulsification purposes in bakery products, beverages, ice cream, chewing gum, etc. So this is your triglyceride. When it breaks to these glycerols and free fatty acid, or sometimes you have monoacylglycerol or diacylglycerol. Okay, anybody wants to give me in the last 2 minutes definition of oxidoreductases? From their name, what do they catalyze? Oxidation reduction reaction, where a substrate is either oxidized or reduced, and there is a transfer of hydrogen or electrons in the presence of oxygen. An example is catalase, where it breaks hydrogen peroxide into H2O and oxygen. So polyphenol oxidase is one of the most troublesome enzyme in food systems, and a lot of work has been done on inactivating it or eliminating it from certain crops. So the impact of that enzyme is basically browning, and sometimes it's desirable, like in tea. Sometimes it's really not desirable. You don't want to eat that shrimp when you see it. Maybe it's not necessarily bad for you in terms of health, but you don't want to eat it. It's not really good. And then, of course, in crops, the browning, if the fruit is bruised, that means the cells are broken, the enzyme is in proximity with the substrate, and browning happens. So Granny Smith, for example, does not brown very fast. Why? Yeah, did I say that before? Yes, it's genetically modified to have a lower PPO concentration in the apples. So this is the kind of the chemistry behind the reaction of polyphenol oxidase. So we start monophenol, react with one type of polyphenol oxidase, chrysolase, in the presence of oxygen to give me diphenol. And diphenol in the presence of catecholase, which is another polyphenol oxidase, in the presence of oxygen gives the quinone. The quinone is the starting compound that leads to polymerization of amino acids and proteins to form complex compounds or polymers, melanin. And these are not, this reaction, the polymerization reaction is non-enzymatic, it's simple oxidative condensation. So you can reverse it by adding ascorbic acid, which is an antioxidant, a reducing agent. So it basically reduces quinone back backwards, so it's going to drive the reaction here backward before it gets into polymerization. Or you can add thiol compounds or sodium bisulfite, which are also reducing agents. So these can be added to kind of reverse the reaction, prevent it from moving forward. Or you can add, sometimes you use sulfur dioxide as a reagent to prevent browning. And the way it functions, so like in dry fruits and stuff, they use SO2 sometimes. And what it does, it forms adducts, sulfur adducts, and these will not be involved in polymerization. There are different methods to inhibit or inactivate this enzyme. Heat inactivation is very common, dehydration, adjustment to pH under acidic condition, it's not favored. So sometimes if you cut an apple and squeeze a little lemon on it, it won't brown very easily. It's a simple thing we've done in the past. So reducing agent, chelating agent, because it's a metalloenzyme, it requires a metallic group for it to function. So adding chelating agent will strip it of that metal group. Aromatic inhibitors, some of them are competitive inhibitors, or aromatic are competitive inhibitors because they kind of simulate the shape of the substrate. Sometimes you have modified atmospheric packaging to strip the atmosphere, change the atmosphere from the gas percentages for the oxygen percentages required for the reaction to occur. Genetic engineering, such as in the Granny Smith, irradiation, time pressure processing. I have two case studies that I will go over next time because I have to go. All right.